Hi, my name is James Herzing. In this simulation in action, Parker Wright is going to take a look at CFD for valves and industrial machinery. Let's go ahead and see what Parker has to say.
Hey, this is Parker Wright with the simulation team, and in this segment I'll be talking about Autodesk Simulation CFD for valves and industrial machinery. Okay, so what is CFD? In its simplest form, it's the modeling of air and fluid flow as it interacts with surrounding solids. CFD stands for computational fluid dynamics. In this case, fluid could be liquid, gas, air, blood, peanut butter, anything we can describe. And dynamics means movement, obviously, to complete the acronym there. So most CFD tools also model the effects of temperature or thermal influences. So today, when you say CFD, you're typically talking about flow and thermal simulation. So here's a quick video. This is using simulation CFD results and showcase. We see the valve, kind of falling apart on the table here, and then we'll see the flow stream come in. We can move or animate the poppet as it goes up and down, or the cage, and look at the actual flow streams within the valve so we fully understand the flow regime. Very visual, intuitive way to share results with clients. Pretty neat stuff there. So why do industrial machinery companies adopt simulation? Well, if we look at the top two pressures referenced in the Aberdeen Group report, number one is a shortened development schedule. So whether it's a small to medium business or a large business, over 50% report the need to shorten their development schedule. Competitive pressures are increasing, costs are going up, we need to get products to market faster, so how do we do that? The other big one is the need to reduce development costs. So doing everything faster and at a lower cost, reducing engineering time, reducing manufacturing time, and reducing the amount of recalls or warranty issues that we have so that we can continue to focus on new product development. All right, so if we look at the average prototype costs and savings, so this chart shows product complexity on the left from low to very high. And on the far right, we can see the costs saved with simulation. So in a lot of cases, if we have low quantities of prototypes, we don't need as much time. The cost savings can be lower. Sometimes these one-off prototypes are very expensive. And obviously, as we get into the higher realm in terms of number of prototypes required, the time becomes significant and the cost is astronomical. So a great way to cut down on your prototyping costs and your testing costs using simulation. All right, so now we'll take a look at one of the tools within simulation CFD that companies use to do this, right? So fast solutions and accurate solutions require good mesh. So within simulation CFD, we've built in technology that adapts the mesh to your actual solution. So again, the key to a good solution is a good mesh. We're providing that to you automatically. So simulation CFD goes in and looks at the actual flow fields, the gradients and velocity, pressure and temperature, and adjusts the mesh accordingly, automatically, to deliver the highest fidelity solution to you. Okay, so how about some of the business challenges with industrial machinery? Well, time and money spent on physical prototypes can be extensive. So we want to help reduce the physical prototyping and testing process because that's expensive as well. Product quality is obviously very important. We can't release products to market that aren't of high quality. If there are recalls or issues, warranty issues, it's bad liability-wise, reputation-wise, and cost-wise. So simulation helps address that. Cost to build and rework products, if we do have recalls or issues in the field, can be very high. And the barriers to simulation, this is something that we hear all the time, right? So, we can't integrate it into our process, or my team doesn't have the expertise. Well, simulation CFD is built to work with your native CAD system. So whatever CAD system you're using, we work with it and we're integrated directly into it. So it's integrated into your process rather than representing a stop in the process. The other thing we hear is that managers are worried about the expertise of their staff. So that's why we have automation built in under the hood in simulation CFD. So there's a lot of very high-end technology within the tool. We have PhDs around the world who are using this tool, but we also have high school students using simulation CFD to design human-powered submarines. So yeah, it's something that can be picked up by just about any designer or engineer. And the last one here is selecting the proper materials. So always critical, especially in the industrial machinery space. So how about some common technical challenges from industrial machinery? So calculating CV curve or looking at valves at different positions. We know this is a common request. So we actually built an app that connects to simulation CFD that will automatically calculate CV values for you. And you can download that from the Autodesk App Store. It's pretty cool, forward thinking. Sizing of equipment. very important, especially with some of the larger equipment, whether it's the actual deliverable or the test equipment can be substantial. So we have to get it right the first time. Testing and data collection can be expensive and tedious. Instrumenting a flow bench or a thermal rig can really be a pain. You only have so much data that you can collect with thermocouples or pitot-static probes or velocity probes. With simulation, you have an infinite amount of data that's accessible to you. It's right at your fingertips. Predicting temperatures, obviously very important. We want to make sure that the equipment and components don't overheat. And being able to predict erosion. So simulation CFD is also used for heat exchangers. Here we have a cross-flow heat exchanger mixing hot and cold water. Shell and tube, that's no problem as well. So whether you're mixing fluid streams or you're using air over water tubes or cross-flow, shell and tube, again, plate fin heat exchanger, all of those are also nice fits for simulation CFD. And then of course electronics cooling. A lot of times with industrial machinery companies, they want to study maybe racks of equipment in a room and understand what the effects are of say a hot machine next to a monitoring rack, and how can we better manage the airflow so that that rack and its expensive electronics don't overheat. So another nice fit. All right, so now let's take a look at the tool in action. So this is a demonstration model that's run out of Inventor. And whether you're running out of Inventor, SolidWorks, Pro-E, CATIA, SpaceClaim, NX, it does not matter. It works exactly the same. But in this case, we'll show it out of Inventor, and we can see this valve body and the poppet and cage parts that move up and down to control the flow. So fairly complex assembly. Again, good fit for us though. So what we'll do is we'll actually run just half of the valve. So this is a symmetric model. We've cut this in half, and in order to have simulation CFD generate a flow volume, we'll put a cap on the front face of this. So now we'll activate the CFD ribbon, and then we'll launch this model, use the native CAD connection into simulation CFD for the analysis. So what we'll see is once we're in CFD, we'll hide that cap part, and now we see that blue fluid part has been created for us automatically because CFD detected an internal airtight or watertight void. So we'll grab each of those volumes, I'll move out of the way here, and assign those to be water. All right, then after that we'll go through it and grab the external body of the valve and assign those parts to be steel. So we have an extensive material database that you can select from, a lot of pre-built materials, the most common ones that we see out there, including liquids, fluids, solids, compact thermal models, fans, pumps, and even LEDs. But you can also create any material that you're using. So if you have maybe a more non-standard fluid like liquid natural gas or maybe jet fuel or some sort of off-the-wall material, that's very easy to create. You just need the density, the viscosity, and the specific heat and thermal conductivity, and that's stored in your database forever. You can see also that we're setting up some of the individual smaller parts within the cage and maybe some of the higher hardness parts as well, where we're going to study erosion. So our materials are done. After this, we'll set up the boundary conditions. So here we're clicking the inlet side on this water part, and we're going to specify a flow rate. And typically with valve studies, we'll specify either a flow rate or a velocity, maybe a mass flow rate in some cases as well. But we'll push a flow rate in on the inlet side, and then on the outlet side, we'll set that to 0 gauge pressure. So that's just a relative pressure indicator. And you can set that to anything you want. You can ramp it up or down in the time domain, whatever your application calls for. And then the last step here for this application is to select those inner symmetry surface faces and assign a slip or symmetry condition to them so that flow can develop all the way up to the face. We don't want this to act as if it is cut in half and has a wall there. We don't want to see any wall effects. We want to see the flow fully developed. So very straightforward setup for valve simulations. A flow rate, a pressure condition, and some slip symmetry conditions. And now the last part of the setup is meshing. All right, so within simulation CFD, we have this automatic mesh technology that goes in and looks at edge length and curvature and assigns the mesh accordingly. So wherever we have more detail, we have more mesh, we have more elements and nodes so that we have higher fidelity, and wherever we have less detail, the mesh kind of relaxes as we work our way away. And this is so that we can maximize the usage of our resources. We don't want to over-mesh it and have the simulation take forever to run, but we want the right amount of detail. So the other capabilities that we built in to ensure that are the mesh adaptation that I referred to before. So we can go in the solve dialog. So we'll activate that now, and we can run this steady state, we can run it transient, we can run incompressible flow, subsonic flow, so Mach 0.3 to 0.7, or compressible above Mach 0.7 to supersonic. And we can also set up this mesh adaptation so that it automatically adjusts the mesh based on the gradients in the flow fields. So here we're looking at results. And we see that red shows areas where the velocity is high, the flow is moving very fast. And blue shows areas where the flow is moving very slow. So we can see that the fluid, the water, jetting up through the small gap and flying out to the side. So we can already guess where we might have some erosion going on. And we can guess where the majority of the pressure drop is as well. But we also want to take a look and understand if there's any recirculation, stagnation, cavitation, things that negatively or adversely impact the pressure drop and our ability to maximize the flow through this valve. Or maybe in some cases we want to very tightly control the pressure drop, and that ties back into the CV values that we referred to before. So how do we find those areas? We can use vectors on this 2D slice, or this cut plane, to show velocity and magnitude. So the magnitude is shown with the colors, and the direction and magnitude. Magnitude is shown with the colors, and the direction is shown with the arrows, with those vectors that indicate the direction the fluid is moving. And that allows us to find areas where it might be swirling around or expanding or contracting very fast. And those are areas that definitely impact the flow solution. Okay, so another great way to look at these is through the use of isosurfaces. So the cut plane was more of a 2D indication of what's going on. The isosurface is a very 3D visual, intuitive way to look at the flow results. So it's essentially a cloud of flow at one value. ISO means one. So here we're seeing everywhere that the velocity is a specific rate. We can expand that, grow that or shrink that. Now we're seeing everywhere the velocity is a specific value, but it's shaded by pressure. So we can see areas where the pressure drop is very high or where it's very low on that velocity isosurface. So again, a really intuitive way to look at it, a great way to share this with external stakeholders as well, because it's so visual. What I like to do typically is overlay a few isosurfaces onto each other so that we can show multiple velocity areas, or in a lot of cases it's very effective to show pressure drop that way as well, so we can kind of show the different pressure regimes as we're working our way through our assembly. But of course the most visual, impactful way to show this and show how the fluid is moving is with trace particles or streamlines or tracers, whatever you like to call them. So we can set up a grid of these trace particles and then very visually track the fluid flow through the assembly. So right here we're looking at streamlines of the fluid. We can assign mass to these as well and turn those into those erosion type particles, but just really visual way to see it. So we're using graphical indication to show multiple designs and show what the corresponding effect on pressure drop is by changing the design. So whether you move the valve up or down, whether you shrink or grow the window, you can increase or decrease the flow rate, but we get that instant response as to what exactly are we looking at in terms of pressure drop and in terms of velocity. And then we'll go in here as well and we will line up multiple simulations that we've run using those trace particles, and we can compare those in one common window or in 3 windows side by side. So we've actually run 3 different designs in this case, and we're comparing each of those all in one interface. So we have 3 different solutions loaded into one simulation CFD interface, and now we're animating through the different valve positions and different window sizes to see what the effect on the flow streams are. Extremely powerful, really, really neat results visualization capability. So I hope this has been informative in terms of how simulation CFD fits into the industrial machinery market. And if you have any questions, feel free to reach out to me directly at parker.wright@autodesk.com. Thanks for your time.